Hello all, welcome to the next lecture on thermal management. So, in the last session we had an overview of the thermal management of the electric vehicle systems and followed by the thermal management in battery pack. So, the battery thermal management is what we have seen and what are the different types of battery thermal management. So, in this session we will be concentrating on thermal management in power electronics as well as electric motors. So, the first one is the power electronics. So, as you know, the power electronic in the power electronics there are various inverters and converters that are present in the hybrid electric vehicles or the electric vehicles which interface the energy sources and the traction drive motor. So, these generate heat during operation and effective thermal management is essential and critical aspect to ensure the reliability, performance and longevity of the components. The major part in power electronic converters is to actually maintain this thermal management effectively for improving its reliability and performance. So, the first one and the most commonly used thermal management system in power electronics is heat sinks. So, the heat sinks are commonly used to dissipate heat generated by power electronic components. They provide a large surface area for heat transfer and can be made from materials with high thermal conductivity such as aluminum or copper. The choice of heat sink design and material depends on factors such as space constraints, weight and thermal performance requirement. When coming to this design of heat sink, as you see, once in case if possible you just go to a electric vehicle shop and open the electric vehicle and see the small converter. So, the converter will be cased in a heat sink case or it will be put in a heat sink case. So, the heat sink case design is very important. Now, how do you design this heat sink case? Again, the heat sink case design depends on the first one, what is the amount of heat that is being produced. So, you have certain calculations for that, you can go through the calculations will tell you how much the heat is being dissipated at its peak power upon providing the ambient temperature and the current flowing through the converter. Now, based on that you should select the volume of the heat sink. Now, when the volume of the heat sink is selected, we must ensure that that particular volume of the heat sink and the volume or the size of your converter should match each other. When it matches, you can just have the converter inserted in the heat sink case and you can use the thermal paste to fix the switch and the diode to the heat sink, which will take care of the remaining heat dissipation part. Similarly, you have another kind of heat sink which does not actually require the complete casing, only the switch gets heated up or only the small part of the system gets heated up, where you can simply dissipate the heat from that part. So, you will have a heat sink designed only for such systems. However, in electric vehicles these kind of systems are very rarely used. The third kind of heat sink design is the complete fin. So, the complete PCB or the system what you have in the converter will be mounted on the heat sink. The heat sink will be the base and that heat sink will have a high fins. So, this heat sink which you are using here will be mounted, will be having the complete system on the top and the switch and diode whatever is there in the converter will be pasted again, will be pasted into the or will be inserted in this heat sink. So, now when the system keeps on operating, the system, the heat that is being absorbed or the heat being generated will be absorbed by the heat sink and will be dissipated into the air. If this system is not enclosed or it is left to air, that is nothing but heat cooling, air cooling. In case if it is inserted in some liquid or coolant to absorb, it is called liquid cooling. We have three different types of heat sinks that have been shown. So, the first kind of heat sink is the heat sink which has been directly placed to the switch or the diode, whereas the second one it shows you the heat sink with fins which is placed to the complete board, and the third one is a case. The third one is called the heat sink case. So, this heat sink case generally has the complete converter or the inverter will be placed inside it, and all the switches and diodes will be attached to the ends of the heat sink using some thermal paste. So, when there is an operation of the inverter or the converter, the power electronic converters, the heat which is produced will be absorbed through the paste and it will be transferred to the heat sink, that is the case, and it will be dissipated out. So, this is the major and widely used thermal management in power electronics. The next one is the liquid cooling. So, in case of liquid cooling, the liquid cooling involves circulating a coolant, which we have already seen. The liquid, the coolant is generally a mixture of water and glycol, and it is circulated through channels or tubes in close proximity to heat generating components. And liquid cooling is more effective than air cooling in removing heat from components with high power density, and it can be particularly useful in EVs where space is limited. So, in a two-wheeler EV and a three-wheeler EV, especially we go with heat sink case. Instead of liquid cooling, we go with heat sink case, because the space the converter has both heat thermal management system as well as the support for the converter, whereas in few four wheelers and even heavy duty vehicles we can go with, or we are opting the liquid cooling. So, this is how the liquid cooling happens in a power electronic converter. So, here there is a heat sink case and beneath it, it is a liquid. So, all the liquid will be absorbing the heat from the heat sink, which absorbs the heat from the upper materials. The next one is the air cooling. So, the use of air as a coolant for vehicle power electronics is an attractive option. The direct use of air simplifies the cooling loop and eliminates the need of a secondary coolant. The figure shows a typical arrangement for using air as the cooling fluid. Ambient air is filtered, then pressurized and distributed via manifolds over micro channel heat exchangers situated near the heat generating sources. In order to be able to dissipate the heat fluxes that are generated by vehicles power electronics, high convective heat transfer coefficients are needed. The micro channel geometries enhance the heat transfer coefficient and increase the surface area that is available for convection cooling. So, this is the schematic of the air cooling system, where the maximum surface is used for convection heat cooling. The next one is the thermal interface material. So, the critical semiconductor elements in an converter or inverter are IGBTs, MOSFETs and diodes. So, the figure shows the different layers how constituting a typical IGBT package in an inverter. The silicon die is soldered to the direct bond copper, which is composed of an aluminum nitride layer sandwiched between the two copper layers. In a typical IGBT package, the DBC layer is attached to the aluminum heat sink via an interface of thermal grease. So, as you can see in the figure, initially in the top layer we have the silicon chip, followed by a direct bond copper and then followed by a thermal grease, and then we have the fins of the heat sink, that is a heat sink. So, these layers completely are used for absorbing the heat from the IGBT or the MOSFET and dissipating it outside. So, the next one is the direct backside cooling. So, in the direct backside cooling, holes are cut through the base plate all the way to the DBC backside. Nozzles are placed under the DBC with coolant jets impinging on the backside. The nozzles are positioned in such a fashion that the jets are directly under the IGBTs and diodes. This design combines the benefit of reducing the overall thermal resistance and applying high convective heat transfer coefficients. this solution eliminates the need of thermal interface material by removing several layers in the stack up. So, this is how it is looking like. So, the coolant jet is passed through the backside holes, and the figure A represents the cross section of the novel package design, and figure B represents the snapshot of the model used for structural and thermal analysis. So, basically the heat sink design itself is a different concept, where we need to undergo or we need to have a study on the power rating of the converter or the power rating of the inverter, then what is the amount of current that is flowing into the system, what is the maximum temperature that the system is being produced or it is being dissipated, the maximum heat and the temperature because of the heat that is being dissipated, along with the other aspect, what amount of area is available in the vehicle, what amount of area does the what is the volume of the heat sink that is required. All these are to be considered when a thermal management system for electric power electronics in electric vehicle is considered. Especially in heat sink and liquid cooling, space is the major constraint. So, before we design the thermal management system, it is important to know what amount of space is available in the vehicle, such that the battery is fitted, the thermal management of the battery is taken care, and the thermal management for the power electronics is also taken care in a very less space. So, the various aspects which are to be considered when we design the thermal management of a power electronic converter or inverter is: the first one, the space availability; the next one, the power rating or the current or the heat or the temperature that is being dissipated when it is under peak power operation; and the third and important one is what is the frequency and the current that is flowing or the current of the converter, the current rating of the converter. So, similar to battery thermal management system and power electronics thermal management system, the other important component in which requires the thermal management is electric motor. So, the efficient thermal management technologies are essential to prevent insulation failure, short circuits, demagnetization and burnout of electric motors, which can result in improved speed and torque. The various stages exist to meet the demands of different heat flux levels. As heat generation mainly occurs in windings located in slots and rotors, thermal management technologies are primarily targeted towards them rather than lamination due to iron losses. To address different levels of heat flux, technologies such as natural air cooling, forced air cooling, indirect and direct liquid cooling and hybrid methods that incorporate thermal conduction enhancement technologies such as thermal paste, heat pipes and phase change materials are to be implemented. So, again similar to the battery thermal management and power electronic thermal management, the four types of motor thermal management are air cooling, water cooling, heat transfer cooling and integration cooling. So, the first one is the air cooling. So, the air cooling, what we have seen in the previous two components or the two systems is the same here also. So, the air convection cooling is commonly used cooling method for small to middle sized electric motors. Ribs or fins are commonly used for natural convection cooling outside the motor and their layouts are under optimization. For internal air cooling, a fan is used to circulate the air in the motor. The optimization of heat transfer in the air gap and air flow path is crucial to cooling performance. The air gap fans to the motor cooling and various fan configurations have been used in various systems to improve the heat transfer coefficients at the winding surface and air gap. A rear fan is also used to cool the motor temperature, and cooling performance of the rear fan was superior to that of the front fan, demonstrating the coupling effect of motor structure and airflow. Although the design of motor cooling by air is relatively a mature technology, accurate predictions of heat transfer coefficients in the air gap and space are challenging. So, the air gap, although is very established, we need to have a more and more accurate predictions of these heat transfer coefficients. The next one is the liquid cooling. In the liquid cooling, currently the dominant thermal management system in electric motors is liquid cooling. Now, why is it so? It is because it has an excellent heat transfer ability. So, from the perspective of the winding, liquid cooling can be divided into indirect and direct liquid cooling. So, the same what we have seen in battery thermal management system. So, in the former, the coolant does not come into direct contact with the winding and its flows path typically involves jacket like serpentive channels in the housing, whereas in the direct cooling we have the direct contact of the windings. We will see how. Now, in the indirect cooling, the water is most commonly used coolant and numerous studies have been conducted on water jacket cooling, making it a mature technology in the motor industry. Ethylene glycol solution is also used as coolant as it expands the temperature range of water cooling. An increase in the turns of jacket channel, the volume fraction of the ethylene glycol and flow Reynolds number increased the cooling performance. Oil is another coolant alternative which is highly compatible with the lubrication system. A housing and stator channel layout for motor cooling with oil has been studied and the structure extended the oil distribution and increased cooling performance compared to conventional jacket structures. So, this is how the water jacket cooling is. So, we have the stator and rotor windings and we have small channels between the stator windings through which the water flows for cooling purpose, and oil spray cooling both have explored as cooling methods. So, the oil jet cooling for end winding is shown in the figure. Oil cooling for end windings has been implemented with oil being ejected to each end of the winding. So, as can be seen, the oil is sprayed or ejected on the ends of the windings to make it cool or to absorb the heat or to dissipate the heat from them. So, oil spray cooling is also being used, and the presence of oil spray helped to maintain the winding temperature within safe limits at a higher heat loads. So, that is what is shown here. So, how is the oil sprayed? It is sprayed through the nozzle into the stator winding, and the oil which sprayed will reduce the inner temperature of the windings. The other solutions that are available include the thermal conductivities of resin and lamination, and the new technologies that are developed are hybrid technologies in which the technologies combine advanced cooling and heat transfer enhancement methods to address extreme scenarios. The incorporation of thermal paste, potting materials, phase change materials, heat pipes in electric motors have also been examined. A motor casing with paraffin waxings is shown in the figure. So, here as seen, the paraffin wax is implemented in between the windings as shown. The stator is there and the film is there. So, in between these two, the paraffin wax has been coated such that it absorbs the heat during the operation, and the presence of paraffin cavities allowed the motor to operate 32.7% longer with the peak temperature at the same heat load. So, an experiment has been conducted with and without paraffin cavities, and it has been observed that with the same heat load, the paraffin cavities are allowing the motor, or the motor has operated for a pretty long time, which is around 32.7% more comparatively without paraffin cavities. Additionally, the paraffin melting temperature also has significantly affected the cooling performance, and in case if we choose a higher melting temperature of the paraffin just below the heat resistance temperature, it will be even more beneficial for heat transfer. Further, we can also have heat pipes in the heat pipes into the casing. If it is incorporated, that also will reduce the temperature of the winding, making it more efficient for operation. So, how is it done? So, the figure here shows the phase change heat pipe which is incorporated in between the windings. So, using heat pipes, the stator temperature increase was substantially delayed by over 20% and the peak temperature was also reduced for both straightly embedded and 3-dimensional rounding heat pipe modules. Furthermore, the straightly embedded layout of heat pipes was expected to dissipate heat more effectively compared to 3-dimensional rounding heat pipe modules. And the last one is the integrated thermal management. So, now when coming to the integrated thermal management, it is the combination of all the things or one or more things. So, in one of the integrated system, coolant is typically introduced to a motor through a hollow rotor and sprayed into the stator and bearings via small holes. And the integrated thermal management technologies that used oil spraying from a fallow shaft for an in-wheel motor is shown. So, here as we can observe, the rotor core, the bearing, the zig, and we have some oil that is being sprayed into the or near the bearing, and the oil which is inserted is sprayed near the housing of the motor, such that the temperature will remain within the limits. So, these are certain various other options that are available with the thermal management system for an electric motor. So, we have tried to understand the different thermal management systems that are used, or we had an overview of the thermal management systems we have that are available for electric motor in an electric vehicle. Now, out of all these things, again which one is more suitable? Now, coming to the suitability of the thermal management system, the same parameters will be considered. The first one is the rating of the motor. So, we cannot use a liquid cooling or we cannot use a highly complex cooling for a two-wheeler. So, the motor rating is to be considered. The space that is given for the motor in the vehicle is also an important aspect. The best way and the cheap way is air cooling. However, the limitations are the limitations of the air cooling, which include that it is not able to transfer the heat throughout the motor winding in a uniform way, and so it should be properly taken care that heat transfer coefficients in air gap and end space are properly maintained. It is very accurate. However, due to this constraint, it is not widely employed for heavy vehicles. Now, what are the other options we have? We had an overlook on that. Further, we also had seen some figures how this motor is actually, or how this thermal management system is actually implemented in motor, and how effective it is with some statistical data, with some experimental data we have seen. So, this concludes the electric thermal management system for electric motor and the thermal management for power electronics. So, in this few things we have learned in this lecture is, the first one is what are the different types of thermal management systems that are available for power electronics and which one is widely used, what are the advantages or what are the specifications that are to be considered when we are planning to implement a thermal management system. It may be for power electronic system or for a e-motor system or for a e-motor. And another thing what we had is, we have understood where to use and what to use. Further, we have also studied how they are being implemented in different cases, like how they are implemented in power electronics, how they are implemented for motor thermal management. and we have also seen few figures or few schematics how it is being implemented. So, this concludes this particular lecture, and as a conclusion for the complete thermal management, we have first initially started with what are the important aspects of thermal management, why thermal management is important, what are the systems that require thermal management, why they require thermal management, what are the different methods that are available for thermal management, and how to implement them is what we have actually started with in our first lecture. In the second lecture of the thermal management, we have seen what are the different thermal management strategies that are available for a battery, how we are implementing it in the battery, which one is well suited. We had a comparison of all the thermal management cooling systems. We also further had a discussion on different thermal management system and their implementation and the required optimum performance or optimal performance. And then we had a discussion on thermal management system for power electronics, and then we had a discussion on the different types, and then followed by a different types of or different methods of cooling in a e-motor. So, this is what we have learned overall in a thermal management system. Now, the question arises, how do we actually do this without actually implementing it in the motor? So, the same what we have discussed earlier, we have to do certain simulation studies before we actually work on the real time model. Now, you might have done some simulations in the previous sessions for maybe power electronics or maybe battery or maybe for battery management system or for the electric vehicle as a whole. Now, in that we need to add an extra component called sensor. Check with some simulation softwares which provide you this component of sensor. So, you should first understand what is to be sensed, how to be sensed, where it is to be sensed. After doing this sensing options, you need to monitor the temperature in simulation studies, and you always try to implement these sensors or the simulation studies at its peak power. Now, why peak power? Because in the peak power only we understand that the requirement of the thermal management system. So, the more the power is, the higher will be the temperature. The higher the temperature is, the higher will be the requirement of the thermal management, and only then we understand which kind of thermal management will perfectly suit the system, the complete electric vehicle system. In case if you are not able to do simulation for the complete system, at least try it part by part. That is, first you take a battery, connect it to a motor. Now, you check when the motor is running at its peak load, what will be the maximum current that is drawn by the battery. Now, what is the maximum current and what is the maximum temperature when the maximum current is being drawn? This will give an idea of the required heat that is to be dissipated from the battery. Like as studied in the battery thermal management, the range of the battery system is to be maintained somewhere from 15 to 35 degrees centigrade. So, you should not have an overcooling, you should not have overheating, it should be in the temperature limit. So, for that purpose, how you should design? You try with all the different, for understanding, for better understanding, you try with all the different cooling methods which are available in the simulation studies. Based on that, you select which one is best suited for what kind of battery, for what kind of power electronic load, power electronic converter, for what kind of motor. You make a system, you make a study, then you will understand the requirement of a thermal management. Along with the requirement of thermal management, you also will understand the design. So, there are various open source softwares also available. You can search in the internet, you will get to know about various open source softwares which actually will help you in understanding the requirement, understanding the calculations that are required for calculating this thermal management. So, here I conclude with the session on thermal management systems and leave the remaining for you to work out on the thermal management, understand it in a better way, try to do more and more number of simulations, more and more number of what you call the experimental studies, at least try to see how it is being utilized or how it is being actually worked out in an industry. Already I have given some information, the remaining is up to you to study it, to understand it. So, thank you.